In section 4.5 we talk about linear equations in 3 variables. So far we've looked at systems in 2 variables only, things that only contain an x and a y, for example. And visually what we're looking at is basically the lines intersecting in one place, not intersecting at all, or lying on top of each other. So visually we really dealt with just 2 dimensions, which was 2 lines, and the cases of when they would have things in common, and whatever ordered pairs they had in common would be the solution for us. So when we look at systems in 3 variables, we're really dealing with 3 equations and 3 unknowns x, y, and z. And each one is visually what's going on, what's called a plane. It's like a sheet of paper. 3 dimensions, it goes on in all directions. So the sheet just continues in all 4 directions and it's called a plane, whereas before in 2 dimensions we just had a line that continued in both directions. So visually each one represents a plane, and we're looking at what the 3 planes have in common. So here are some of the possibilities that could visually happen when we look at these 3 planes and see what they may have in common. The 3 planes could intersect at one location, like a dot here, which is actually called a triplet, and it's represented similar to an ordered pair with 3 components, x, y, z, or whatever your 3 variables are. So that could be one of the cases where they all intersect in one location, one triplet. And this could be imagined like if you're in a room looking at the corner of where the 3 walls meet in the ceiling, that would be a triplet, a location where all 3 planes, the 2 side walls of your room and the ceiling, may meet. The next thing that could happen is you could have an inconsistent system. So this of course is a consistent system because we actually see what they have in common. An inconsistent system because the 3 planes, so the solution is actually a line. In this case we have one solution. Here we have no solution. And here we have infinitely many solutions. The one that we're going to focus on mainly is the first one, where we find a solution to be a triplet. Given the system with the 3 equations, is the triplet 1, 2, 3 a solution to the system? Well, we have 3 equations. Remember, a solution means the triplet that they all have in common. So I have to go check it into each one of the equations and see if I get a true statement. The minute I get a false statement in any of the equations, I stop and I say, no, this is not a solution. So again, I repeat, it has to definitely work for all 3 of them. So we go and we plug in 1, 2, 3 into the first equation and we get a true statement. We plug it into the second equation, simplify, and we get a true statement. And that gives us motivation to continue, so we continue and check the last one, and that also works. So our final answer is yes, this is a solution to the system. This is the easier case where you have a possible solution, you put it in, you check and you say yes or no. Actually finding the solution on our own is much more work. So how do we find the solution to a system on our own? Just a visual of what happens. There's different ways you can do it. But you want to organize your thoughts so that you don't go in circles because there are more variables. You basically start with 3 equations and you pick 2 of them, any 2 you want, and you make a 4th and a 5th equation where the 4th and the 5th equation have the exact same variables. So your goal is basically to take 3 variables from here and get rid of one, maybe using the elimination method, and end up with one equation that only has 2 variables. And then use another 2 equations to get rid of the exact same variable you did before and get a 5th equation that matches up with the 4th equation having the same 2 variables. And once you have that, it's like a system from the previous sections where you can eliminate x or y or one of the variables and find the value for one of the variables. Then you go back and find the other variable that was in the previous step, and then from here you go back and you find the third variable. So you kind of retrace your steps backwards, but the overall logic is that at this spot you have 3 variables that you don't know about. At this spot you have 2 variables that you don't know about, and at this spot you have found the value of one of the variables. And once you find that value, you trace your steps backwards and you get the next one, and then finally the third one. So some of the examples will involve all of these steps, and some of the examples will be easier where we won't have to do everything to find a fourth and a fifth equation. Solve the system. Now this is good news. When you see some of the variables missing, it means it's less work than I've shown up here. You probably have get away with less work in finding all the variables. So this system is missing some of the variables, which is good news. And notice the very last one helps us find one of the variables right away. So might as well start with that one because it only has one variable. Right away we can tell what z is. So we found z, we're good to go. My next goal is to find either x or y, and if I go into the second equation, I'm in better shape because I put in the z and I automatically get the y. If I jump ahead and I go to the first equation, I will still have some issues because I don't know what y is. So it's best for me to go back to the maybe quote-unquote smaller equation with less variables so I can find the other missing piece. So now I'm going to go to 2 and plug in the value of z, and that'll help me find the y value to be -1. So now I'm in good shape. I got the y, I got the z. I just need to get the x value, and that tells me go to equation 1 that relates all 3 of them and plug in your y value of -1 that you found down here and the z value of 1, and you should be able to find x. So this system was a little bit less work because some of the variables were missing. Now I have my triplet 2, -1, and 1, and I'm good to go. Again, if I want to check to make sure this is correct, I plug it back into all 3 equations accordingly and make sure I get a true statement. Solve the system. Again, when I'm looking at the system, some of the variables are missing, so that's good news for me. It's not as easy as the previous system over here because in that one I could automatically get the z value. Here, in none of them I can really get the value right away. So I have to choose 2 of the equations to eliminate one of the variables. And right off the bat I see that these x's have opposite coefficients and sign, and if I just add them, the x will disappear from 1 and 2. So I'm going to use basically 1 and 2 to eliminate x. That's my goal, and it looks like I'm going to get more than my goal actually, because when I add them, not only do these guys go away, but I get, buy one get one free. This guy goes away too, so I end up with y equals -1, and before I know it, I already have the y value. Now that I have the y value, I go wherever I think is useful for me to find another missing piece. And it looks like 3 would be a nice place to go to because it only has one other unknown, which is the z, so this guy goes into 3, and very quickly I can find the z value for this one as well. Looks like z is equal to 2. So this is good news. We got the y right away, we got the z. Now that we have y and z, it looks like I should go maybe either to 1 and use both of them, or I could even go to number 2 if I want to and just use the z I found to get the x value. That might be less work. Go to 2 because it relates x and z. Plug in 2 for your z, and it looks like x is equal to +1 if I divide both sides by a -1. So we got our x, y, and z, and our solution is 1, -1, and 2. Okay, solve the system again. And I have 3 equations, and not too many things are missing, just the x value is missing in the third one. So I kind of have my eye on the third equation because it's missing an x, if I could just find another equation that's also missing an x, then I will be in business. So what I'm going to do is I'm going to use 1 and 2 and eliminate x, just because this guy also doesn't have an x in it. Now it would be easy to eliminate y here, but I don't want to because I would rather find something that I can recycle with equation number 3. So I'm going to take the first two equations, and it looks like in order for me to get rid of the x, I have to multiply everybody in the top equation by a positive 2. And when I do that, I get this new equation. I use the exact same equation from the bottom. We have to do our work very carefully because one little mistake in these problems just has a ripple effect. So these guys go away and I get 3y minus 4z equals 23. And I'm going to call this equation 4. And this equation 4 matches up with this equation 3 because now they have the same variables going on. Now I'm going to use 3 and 4 and see what I can do with these guys, and it looks like I'm in business because even the coefficients of the y's nicely match up for this problem. I don't really have to do any work, but go right away and add them. That's going to give me negative z equals a positive 2, which means z is a negative 2. So after some work, I found my z value. Now that I found my z value, I have to go somewhere and find another missing piece. Well, I can either go to 4 because it only has a y and a z, or I can go to 3 because it only has a y and a z. So I'm sort of retracing my steps backwards and not jumping ahead too much. So I'm going to go to 4, I guess, and plug it in. And when I go back to 4 and plug in this z equals negative 2 into here, I solve it, I get y equals 5. Now I have my y value. I have my y, I have my z, I can go to 1 or 2 and find my x. I'm going to choose to go to 1. So when I go to 1, which was right here, I use it to put in the z and the y value that I found. And once I plug them in, I get x equals 0, and I got my third variable as well. So my triplet is 0, 5, negative 2.